you don't usually get a hand like that before you've said anything. So let's hold your applause till the end and then say what you think. The speed of light is something that we now know a lot about, but this is how we came to know it. The first question that you have to think about is, does light have a speed? Well, okay, we all know that it does, but how do we know? The reason we know is because people told us, okay, or we read it in a book. But what in your everyday experience would even make you ask the question? Why would you even think light has a speed? Now you can think that sound has a speed because if you associate lightning and thunder, which people have done for thousands of years, you know that you will see a flash and then there's some period of time elapsed before you hear the bang. The closer you are to the flash, the sooner you hear the bang. So they knew that that was a difference. However, does light itself have a speed? And it took some doing just to even ask the question. Aristotle had some thoughts on that. He said that light is a property of what he called the ether. You probably remember that the Greeks said there were 4 elements: earth, air, fire, and water. Well, there was a 5th element, and this is the ether. The name comes from a Greek verb, eithane, which means to burn or to shine. So from Aristotle's point of view, light was a property of this shining substance which filled all of the universe. It was not a thing. Because it's not a thing, it can't travel. They thought about, well, if light has a speed, you should be able to detect it. That is, over a short distance, they knew that you could not. But what about a really great distance from east to west? Now that's a very vague term, but say east is where the sun rises and west is off in the opposite direction, say a mountain range. If light has a finite speed, they thought, when the sun peaks over the horizon, it should be light in the east, but still dark in the west. But it wasn't, because the light got there that fast. So they said, well, then light doesn't have a speed, light is just there, okay? Move forward now into the 17th century. Rene Descartes was a French mathematician and philosopher. He was a guy, he would never walk in front of a horse because that would be getting Descartes before the horse. But he thought that the speed of light is infinite because his conception of space, that is what's between the planets, between all of the objects beyond the Earth, he called it a plenum. That means, from a Latin word meaning full, and it's completely filled with matter. He said the first element, what he called the first element, is stuff, it's matter, it's what we normally think of as things. But the second element, he thought of as tiny little spheres that filled all of the space between the first element, and there would be, through abrasion, particles falling off of the spheres that would fall into the spaces between the spheres so that it would be completely filled up, completely solid, and that this is how light would be transmitted. He said, just as a blind man using a cane, he taps the cane on the ground and he feels the ground because it's transmitted through this rigid object. Well, the plenum would be completely rigid, filled with matter, and that's how light is transmitted. He proposed a thought experiment. That is, say light does have a speed, say it's really, really fast, It's so fast that it can travel between the moon and the Earth, or vice versa, in as little as half an hour. Okay, that was unimaginable when the fastest anybody could go in his time was the speed of a galloping horse. So we know that the moon moves its own distance, its own diameter per hour, approximately per hour, as viewed from the Earth against the background of the stars. And you can observe this yourself. Just go out some night where the moon is out, note where it is against the background of the stars, check it again in an hour or so, and you will see that it has moved to the east about its own diameter. Well, if that were the case, and it took half an hour for light to travel from the Earth to the moon and then back, we could not see an eclipse, because the moon is eclipsed by the shadow of the Earth when the sun, the Earth, and the moon are all lined up just like that. So therefore, he said, the speed of light is infinite. Well, that's not a good conclusion. It's the proper conclusion would be light, if it has a speed, it travels faster than that. So Galileo, he was about 30 years older than Descartes, but roughly contemporary. And Galileo said, okay, instead of just making stuff up, why don't we actually do an experiment? This is a new way of thinking. People did not think, that is, academics and prominent people who wrote books and gave talks didn't think like this in that period. This is the beginning, the Renaissance, the rebirth, not just of ancient learning, but the rebirth of critical thinking. Instead of it all being based on a priori notions and philosophical conclusions drawn from these, let's observe what's going on around us and change some variables and see what we can learn.
Call it science.
Yeah, well, science, I'm not sure when the term science actually was coined. It was a little later than that.
Natural philosophy.
It was called, yeah, and in fact, that's what natural philosophy was, part of the title of Newton's great work, the Principia, because it had the natural philosophy was part of the title, but natural philosophy is what we now call science. This is what Galileo proposed and actually carried out. He was on one hill. He had an associate on another hill about a mile away. And the idea was each had a lantern with a shade on it, a lid on it. He would open his, he would start a timer, probably a water clock, we're not really sure. Water clock, I don't mean, water clock in Venezuelan slang, the water clock is a toilet, all right? Not a water closet. But a water clock, that is, you measure time by the speed at which water drips from one container into another, and you measure the water and you've got the elapsed time. We don't really know what his measurement apparatus was, but anyway, the idea was he opens his lantern. When the guy on the other hill sees that, he opens his lantern, and then the time elapsed gives you the speed of light. Well, the result was, to us, predictable. He couldn't tell any difference. So they tried it over several different distances and kept getting the same result. And Galileo's conclusion was, well, this is the light travel time. We know, okay, over 2 miles is like 1/100,000th of a second, something on that order, whereas average human reaction time is about 0.3 of a second. So Galileo's conclusion was, if it is not instantaneous, it is extremely rapid. I should call it momentary. So he didn't say it's infinite. He said
Fast.
It's really, really fast. The Florentine Academy repeated his experiment several years later. Galileo did that sometime between 1630 and 1638. He proposed it in 1630. He wrote it up in 1638, so I'm not sure. Somewhere in there is when he actually did it. So about 30 years later, the Florentine Academy tried it again, but this time separated by 10 miles, and they used telescopes, and they got the same results. Move forward a little in time. There was a Danish astronomer named Ole Rømer. He built on Galileo's work, but what he wanted, the work that Galileo did that he built on, was the discovery of the moons of Jupiter, the 4 large moons of Jupiter, the so-called Galilean moons, named after Galileo. And by the time Ole Rømer came along, people had worked out the times of the orbital periods of these moons of Jupiter. They were known to fairly fine precision. This is a photograph of at least a couple of them. There may be one other one in there, but that's what it looks like through a pretty good telescope.
You want to point, you didn't point to them.
Oops, get the pointer. Okay, there's one of them, and there's one almost off the screen here in this picture. There's one, this is either another one of the moons. I don't think so. I think that is probably one of the white cloud tops on Jupiter. But at any rate, there are 4 very large moons of Jupiter. They're very easy to see. You can see them through any telescope, even a very small telescope. You can even see them through binoculars. I remember I got a pair of binoculars when I was 16 for Christmas, and I went out back, and Jupiter was up, and I braced my shaking hands on the crane. It was my dad had built a barbecue pit out. It was a brick barbecue pit out in the backyard, and had a crane on there that you could raise and lower a grill. And I braced myself on that, and I looked at Jupiter, and bam, there are the moons. And I saw the moons of Jupiter, and I thought, well, how cool is that? But I didn't get into astronomy for another 23 or so years. Other things happened in between there. So in 1676, Rømer found that these timings that everybody had thought were so precise were off. And what he realized, by this time, the Copernican theory of the planets going around the sun rather than the other way around, everything going around the earth, was well accepted, not actually proven. That took some more, and we'll get into that shortly. But the eclipses were happening earlier, when the Earth was approaching Jupiter, and later than predicted when the Earth was moving away from Jupiter like this. And you can see here the Earth at point A Earth is moving in this direction, and Jupiter moves in the same direction, but it moves much slower. Its orbital period is almost 12 years. So in the 6-month period between these two observations, Jupiter has moved about 1/24 of its orbit. So this is the distance for the first observation, and this is the distance for the second observation. And so Rømer realized that the only thing that made any sense was that light did have a speed, and the difference in the timings corresponded to the light travel time across the width of the Earth's orbit. He found the difference in timing to be 22 minutes or 1,320 seconds. And the best figure he had for the diameter of the Earth's orbit was 182 million miles. So he divided that by the 1,320 seconds, and he came up with a speed of light of 137,800 plus miles per second. And this was just an unimaginable speed. But that was the first start on the actual calculation through observation of the speed of light. Now, later refinement of his observations came up with a better figure for the minute difference between greatest and least times, and came to got a better figure for the speed of light. But this was the first example, the first time that anyone had actually calculated it using scientific observation. Here's the big thought that comes from that. We see things not as they are, but as they were. This means here and now, but the difference is negligible. Well, the speed of light between the back of the room and me is negligible, but over very great distances, you look back in time, and George Lucas said a mouthful when he said, a long time ago in a galaxy far, far away, because when you see a galaxy far, far away, you are looking back in time a very long way. One of the closest big galaxies to us, the closest really big galaxy, is the big galaxy, a great galaxy in Andromeda, M31, Messier number 31. Light from M31 takes about 2.5 million years to get from there to here. Not only that, it's so big that light from its far side takes about 500,000 years longer to get to us than light from the near side. That's the effect of the speed of light. That tells you how long ago you're looking back in time, and it's one of the close ones. We look back in time now billions of years. Again, light traveling at 186,000 plus miles per second, 300,000 kilometers per second. So a long time ago in a galaxy far, far away, yeah, this has profound implications for cosmology, because what we're seeing is what happened a long time ago. We see a supernova. That didn't happen as we see it. It happened generally many millions of years ago. And the farther out we see it, the longer ago that was. Moving forward in time a little more, an Englishman named James Bradley was trying to observe stellar parallax to confirm or refute the Copernican theory that the Earth travels around the sun. It was generally well accepted that the Earth did travel around the sun, but there were still the skeptics who said, yeah, but if it does, you should be able to see a difference in the position of a star from one side of the Earth's orbit to another. Parallax, the common example is to hold your thumb up at the end of your arm and look at it closing one eye and then the other eye, and you'll see your thumb appear to shift with respect to the background. This is what we're talking about with parallax. So he tried to observe stellar parallax to show that the Earth really does orbit the sun and to find distance to the stars, because if you can measure parallax, then you can use trigonometry and calculate the distance to that star. Well, what he found was in 1728, he was observing, this dude is observing from London, and he attached a telescope vertically to a chimney. And he would observe stars as they passed overhead. He wanted to have it directly overhead. And what he found was that stars, if they were perpendicular to the ecliptic, which he couldn't really see at his latitude, London is about 50-something degrees north latitude, to be truly perpendicular to the ecliptic, you have to be on the Arctic Circle or the Antarctic Circle. And if you were on the Arctic Circle, what you would see is not what he saw, which was making small elliptical motions. Actually it is, because we see a circle, which is a special case of an ellipse. It's just with an ellipse with an eccentricity of 0. At his latitude, it described a small oval, a small ellipse in the plane of the ecliptic, which would be at at his latitude, from if you were on the Arctic Circle, then it would be at the latitude of the Tropic of Capricorn, 90 degrees away. You would see motion just side to side. There would be the ellipse, the eccentricity of the ellipse would be 1, okay? That's not how parallax should appear. He saw these, parallax looks different, and I'll give you some examples of that in a minute. What he came up with was the idea of aberration of light. That is, to compensate for the Earth's motion, he knew the Earth was moving around the sun. You have to angle the telescope slightly, and based on the known velocity of the Earth in its orbit, which is about 18.9 miles per second, he calculated the speed of light as 188,500 miles per second, which is not too far off the modern figure. Well, here's what we're talking about with stellar parallax. This is what you would observe in parallax. Observing in January in the Earth's orbit here, from uppercase A, looking at that star, it would appear to be at lowercase a, okay, opposite your position. 3 months later, in April, it would be about here. 6 months later, July, uppercase C to lowercase c. So it's in the opposite position of the Earth, and also the size of this ellipse depends on the distance to the star. The farther away the star is, the smaller the ellipse, and of course the closer it is, the larger it is. That's not how aberration looks. This is aberration. In January, it's about a quarter of the way, exactly a quarter of the way around the ellipse. In April, it's back over here, and in July, it's back this way. So the aberration in stellar position is offset in the direction of the Earth's motion, not the opposite, and the size of the ellipse is independent of the star's distance because it's a reflection of the Earth's orbit.
Bill,
Yeah.
all he did was just to prove that all the stars are at the same distance, like on the crystalline sphere
Yeah.
that Aristotle had.
Yeah, and he actually did confirm the motion of the Earth by doing this. It was not parallax, it's not what he aimed for, but it was an indirect proof of the Earth's motion. So this is the most common earthly example of stellar aberration, or the analog. That is, if you're standing in the rain is falling vertically, there's no wind, you're standing still, you can be under the umbrella and it's not going to hit you. But if you walk forward without angling the umbrella, you're going to walk into raindrops. So this is why you start to run, and the faster you run, the more you have to angle the umbrella to keep the rain off you. The same thing applies to light from a star. If the Earth were stationary, the light would come straight down the telescope, but the Earth is not stationary, it's moving, and so you have to angle the telescope a little bit ahead, or 20 arc seconds or so ahead of the true position, in order to see the star. And that's the aberration of light. And based on that, he calculated a pretty good approximation of the speed of light as we know it to be today. So now we've measured it a couple of times, at least a couple of times, by astronomical methods. Pretty good agreement. Could we measure it on Earth? In 1849, a French physicist named Armand Fizeau used a kind of a different variation of Galileo's method, but from here on out, it's all done with mirrors, okay? Instead of having a second man on a hill some distance away, he put a mirror there, and he had a toothed wheel through which he shined light. He sent the beam of light through gap A to the mirror, which was 5 1/3 miles away, and he set the wheel so that it would return through gap C. He knew the speed of the wheel's rotation and the distance that the beam traveled, and from that, he calculated the speed of light to be 194,489 miles per second, which is about 5% high from what we know it today. But At least he proved that you could do it over on Earth. You did not have to rely on astronomical measurements. He also pointed out that lines should shift in the spectrum toward red if the object was moving away from you, or the light source is moving away, or blue shifted if it's moving toward you or you're moving toward it. It would be a couple of decades before this could actually be demonstrated, but theoretically he showed that this should happen, and he called it the Doppler effect because Doppler had already worked this out for sound waves. The famous example of what Doppler actually did was to station members of a military band on a train car, and they were trumpeters, and he had them blow the trumpet for a designated note as the train passed, and it would go, what we now know, this, that's a Doppler effect, which I think you have to differentiate the Doppler effect from the Doppler effect. The Doppler effect is the idea that dumb ideas seem more plausible when they come at you quickly. Which is kind of related to a related concept is the boson layer. That's it's an impenetrable cloud surrounding the heads of willfully ignorant people such that ideas cannot penetrate. In 1850, Leon Foucault had tried going to medical school, but he couldn't stand the sight of blood. So instead, he became a physicist. He was a lab assistant to Fizeau, and he improved on Fizeau's method. He used a rotating mirror. You can see here the schematic of his apparatus. He had a light source here, probably not a candle, but well, actually it may have been at that time, a candle or some similar flame. Anyway, the initial beam went to this rotating mirror, reflected off a fixed mirror, and came back here to measure the angle, and from that he would calculate the two mirrors reflecting over a total distance of 10 miles, and he calculated a speed of light, again, is really pretty close to the modern value. Foucault also had a varied career. He also demonstrated the rotation of the Earth by his famous pendulum. It was a pendulum, and I forget the height from which he suspended it, but it was like from the top of a church dome, and it would trace out in sand, would trace out a circle over a 24-hour period. There is one, I've seen a Foucault pendulum, I think it was in Nashville, at a museum there. I think they have it there. And one of our, Dan Bundo, who's here tonight, a number of years ago built a miniature Foucault pendulum and demonstrated it to us in one of our programs, been quite a few years ago, but it was on small scale, but it demonstrated this is the principle behind the Foucault pendulum. Another of our former members, who was a physics professor at then Memphis State, decided to do a makeshift Foucault pendulum, and the weight at the end of the probably wire, he used a jar of mercury, and he underestimated the distance it would travel, and it smacked into a wall and broke. And then you had a hazardous material spill that had to be cleaned up. Foucault also, another of his many accomplishments was to develop a method of evaporating silver onto a glass mirror. Before his time, mirrors in telescopes were made of metal, and they had to be finely polished. They would tarnish easily, and then you had to remove the tarnish, and when you did that, you would often alter the figure of the mirror, that is the reflecting surface, and you would have to regrind the mirror, and it was unsatisfactory, and so he found a way to put silver onto glass. Glass was a lot lighter, it was much easier to shape, and redepositing silver did not affect the figure of the glass. We don't use silver anymore, we use aluminum now and seal that, but that was another contribution of Leon Foucault. Albert Michelson, an American, actually he was Polish born. His father moved to the United States to escape persecution in Eastern Europe. Improved on the Fizeau-Foucault method, and in 1878 he got an appointment to the Naval Academy, and he was tops in his class there in optics and physics, and he was kind of down the list in seamanship, and the admiral who was the the superintendent who had commanded the Union ironclad Monitor in its famous battle with the Confederate ironclad Virginia, which had been, it was renamed from the Union ship Merrimack, which had been captured by the Confederacy and altered considerably. The Monitor and the Merrimack, which is more alliterative and sounds better, that's what we know it as. The superintendent was the captain of the Monitor, had been the captain of the Monitor during the Civil War. And he told Michelson on graduation, he said, well, you know, you did really well with the physics. He said, if you do as well with the seamanship, you might have a future. So in 1883, a few years later, after he studied optics in Germany and France, he tried again. He got another figure for the speed of light, and there it is, 186,320 miles per second, which was the best value until 40 odd years later, when they designed a new and better apparatus. And this is what it was. This is also done with mirrors. It was done over a distance of 22 miles from one mountain in California, Mount Wilson, to Mount San Antonio. It was surveyed to an accuracy of less than an inch. And the mirror, clearly not to scale, but you had the light source here. It would bounce off this face of an 8-sided mirror to the fixed mirror 22 miles away back to be, and again, you knew the rotation speed of the mirror. It was adjusted to rotate exactly 1/8 of a turn during the round trip. So knowing that distance and the rotational speed of the mirror, this is the speed that he got, and this is the currently accepted speed of light. He got 186,285 miles a second, and the accepted figure is about 3 miles a second less than that. So really not bad at all. Then he teamed up with Edward Morley to do another experiment, and this time it really was not so much about finding the speed of light. They knew that pretty well. James Clerk Maxwell had, in his famous series of equations demonstrating the electromagnetic nature of light and other, well, what we now think of as radio waves and so on. It's all part of the electromagnetic spectrum. Light is just one part of it. He had suggested an experiment in 1875 to see if light has a constant speed, because we knew it was fast, okay, we knew about how fast, but did it vary? They believed that some medium of propagation was necessary to move light waves, transfer light waves, because the wave nature of light was well established, and the analog was water waves or sound waves. And if you drop a stone in the water, you'll see waves moving out from it. Well, the water is the medium through which that energy travels. Air or water or steel or whatever material can transmit sound. So there's a medium there that transmits the sound, that propagates the sound, and they call that the luminiferous ether. Okay, remember Aristotle's ether? Luminiferous from the Latin meaning light bearing. This is the means by which light is propagated. And one of the thoughts on this was, because of the Earth's motion, light should be slowed by what they call the ether wind. That is, if you move, okay, if you ride a bicycle, you make your own wind. If there's no wind, You create air resistance. The same thing, an airplane moving through the air creates its own wind. That's the function of a propeller on an airplane or a jet, is to move it forward so that the design of the wing will work out to call it Bernoulli's principle, that the pressure under the wing is less than the pressure on top of the wing, so you get lift. But the ether wind was thought to be there because the Earth is moving through this luminiferous ether and creating its own wind, and that therefore the speed of light in that direction should be slower than at right angles to that direction. So in 1881, Michelson built an interferometer to test this. And this was the experimental setup here. This was not on a grand scale. The total light path on this is 11 meters, okay? But they're not timing it. What they're doing is looking for interference fringes. The light source was here. There's a half-silvered mirror here at M. Part of the beam is reflected off this mirror to a second mirror here, and then back through the half-silvered mirror down to a telescope here. But part of the beam, the part that is not reflected this way, goes through the half-silvered mirror to a second mirror, and he put a second pane of glass here of the same thickness so that the path of the light would have to go through the same amount of glass, because glass itself will slow down the speed of light. That was known. And then be measured here, and then the idea was you should be able to see a shift in the fringes from if there's interference, if wave crests come together, they amplify, and if they negate each other if you get a trough and a wave together. So you get a fringe there, and that's what you should see if in the direction of the Earth's motion and the beam perpendicular to it, but they didn't see a shift. And when they actually set this thing up, they built this apparatus on a big block of wood. They floated the wood in a tub of mercury so that it was isolated from ground motion and so on. And it was also much easier to turn it. And they turned it through various degrees to see, well, maybe there's something peculiar about this direction, so let's try it this way. And they tried it through a number of different positions. No fringe shift. They tried everything they could do to see if they could get the beam to slow down, and they never got a fringe shift. So, how come? Physicists have tried other explanations, including say, well, the arm in the direction of the Earth's motion had somehow contracted. It was shorter, so that shortened the path of that beam and made the measured speed the same. Ernst Mach was, for whom the Mach numbers are named, the speed of sound exceeding the speed of sound, was a rugged empiricist. He said that if you can't see it and you can't measure it, it's not there. And he extended that to atomic theory. He did not believe that atoms made up. There was a theory that atoms made up everything that there is. He didn't believe it because you couldn't see it and you couldn't measure it, at least in his time. But he said, okay, the ether does not exist. And that set the stage for Einstein. In 1905, with his special theory of relativity, in 1905 was the annus mirabilis, the wonderful year in which he published 3 or 4 just earth-shattering papers. He said, okay, the speed of light in a vacuum is a universal constant, and he based this also on Maxwell's equations, and he said, you don't need the ether. And Michelson, whose work actually made Einstein's possible, never accepted relativity. And so far, every prediction that Einstein made from special relativity and general relativity 10 years later, every one of them has been confirmed, nothing has contradicted anything that Einstein predicted. including things that he didn't believe himself. He did not believe that black holes would exist. His equations showed that they should, but he didn't believe it. And they also showed that there should be gravitational waves when enormously massive objects collide, like black holes or neutron stars, none of which were known to exist in his time. But he said, well, that's a curiosity. Yeah, you know, maybe so, but we'll never know. But we do, because they built the laser interferometer, two of them in the United States, and there's a third one now in Italy. And we have confirmed that gravitational waves do exist, and we know from observations what the masses of the colliding objects were, and we have a better idea now about creation of heavy elements and so forth, and all of this flows from Einstein, and a lot of this was based on Michelson and Morley's experiment. Every prediction he has made has been confirmed. And that would be a good time for me to shut up. Yeah, Bill.
Yeah, I tried a little trick once. It actually came to me while I was talking to my astrophysical chemistry class, and that was that Ola Rumor's first experiment on the when the Earth was approaching Jupiter, the eclipses came early, or transits or whatever was measuring, and then later when it was receding, it follows the exact same thing as the equations for the redshift, the delta lambda over lambda, the change in time over the total time is it works out exactly the same way.
Yeah.
So he was actually measuring the Doppler shift when he was doing that.
Yeah. I had not thought of that. Yes. Yeah, Dan.
There is I can't think of the name of it right now, but there's a biography of Albert Einstein. And it's an interesting book because you can read every other chapter and get just, you know, his history, or you can read the odd chapters and get all the mathematics and everything else. And at the very end, they note that there are some of his notebooks that have calculations in it and nobody knows where they're going. He just stopped working on them. Mathematically, they are correct.
Yeah.
But no one knows what the end of.
Well, he spent after the general theory of relativity came out in 1915, and then was the first major predictions we mentioned earlier was the bending of light by the sun. The next thing he tried to work on, and really spent the rest of his life doing it, was trying to come up with a theory of quantum gravity. Quantum mechanics was just beginning to be developed in that period, and relativity works on the macro scale, but on the quantum scale it doesn't. And that's never been resolved, and Einstein spent he tried to come up with a unified field theory of gravity. It took him the rest of his life, and he never got there. But that's, that is kind of the story with a lot of brilliant theorists and mathematicians. In their youth, they come up with these blinding insights, and then that's it, man. They don't do a whole lot thereafter. And I had when I was in the faculty senate at what's now University of Tennessee Health Science Center, then there was, I forget what they called it at the time, the medical units or whatever. It's changed its name many times. I chaired a committee that negotiated the tenure guidelines for faculty. And some of the hardest work I ever did, because that is such a contentious topic on a university campus. It's almost as contentious as parking, and I served on the parking authority as well. But I was talking about tenure with a young faculty member. I think he was in physiology, I don't remember now, but he was pointing out how important it is for faculty members to prove that they are really know what they're doing, that they're worth keeping around, to give them tenure, because of this phenomenon that so many of them do brilliant things while they're young, and then as they get older, they don't do the brilliant things. Still teach, and they'll be, contribute valuable services to the university, but they're not going to come up with these blinding insights much more. And so, I was not eligible for tenure because my position was funded from grants and contracts rather than state dollars, so I didn't really have a dog in that fight. And I was kind of the ideal person to work this thing out. And we did, and the tenure guidelines are what they are, and I'm told that what we worked out back in 1976 or so became the basis for the University of Tennessee system tenure guidelines. I couldn't swear to that, but that's what I'm told. But again, that was some of the hardest work I ever did, and it was something that, it's nothing you train for. It's just you get in there and you do it. But at any rate, that's kind of getting off the subject here, but about the future accomplishments of brilliant young men, sometimes that's all they got.
And my professor told me if I didn't do something by the time I was 25, then just forget it.
Yeah.
And Aristotle might still be right. We still haven't discovered really what is dark matter and dark energy.
Well, Aristotle, I don't think he even imagined dark matter or dark energy. No, we don't know what it is, and it's the thing about the dark part of it is not as someone pointed out. It's not just that we can't see it. We can't, but it's dark metaphorically because we don't know what it is.
Yeah.
Well, in quantum field theory, the Higgs field is about as close to the ether as you're really going to get. That amounts to
For a short distance.
Okay, anybody else?
That wasn't my idea, by the way.
Okay.